Okay, so here we are going to compute the RLB and RUB, which should be something, based on my computation, this is 31.25 and this is 105.25, and thus any data point that is less than 31.25 and any data point that's larger than 105.25 is an outlier. And here you can see that, do we have any? Oh, actually, yes, we have this outlier here because it is lower than 31.25. Do we have any others? We have this one here too, 25 as well. Do we have any more? We have 30. These data points are less than the reasonable lower boundary, and thus we have to determine them as outliers. So explain your answer. What I'm expecting from you here, explain your answer, is for you to explain, since these values are less than the RLB, then they are outliers. As simple as that. Okay, moving on. Number 2. 45% of children in the school have a dog, 30% have a cat, 18% have a dog and a cat. What percent of those who have a dog also have a cat? So be careful with wording here. So let's first translate this into the correct statistical notation. That's the first step that you need to do. So if I determine that D is the event in which a child has a dog, and then I have C, the event in which a child has a cat. I know, so I know that the probability of D happening has a dog is 45% or 0.45. I also know that the probability of C happening, having a cat, 0.3. Next, I know that 18% have both a dog and a cat. So I know the probability of C and D, or I can also write this as the CD, is 0.18. The question is, let's try to get through it. What percent of those that have a dog also have a cat? So this is implied that now I know that they have a dog. What is the probability of them also having a cat? So if you recall, I can compute this using conditional probability. What is the probability of a child having a cat if I know that they are those that have a dog as well? So here we have to put out our friendly neighborhood conditional probability formula, and then we can obtain 0.18 over 0.45. You can use your calculator to compute it. 2/5, I think, should be. Or you can use your calculator 0.4 or whatever. Next. This is probably the one that got you a little bit in a bind because the calculus is coming in. So let's look at this question. I know that I have a PDF for a random variable X. I don't know what it is. It doesn't matter. I know that I have the probability density function as follows. So first, I ask you to please determine the value of K so that it is a valid PDF. And I would like you to compute the value of X being smaller than 12. I apologize. I hope I wrote it correctly in the question. Oh, I did not. Okay. So guys, let me look at your answers for a sec, because to be honest, this is a typo. It should be a large X and not a small x. So my apologies. Let's peek at one of your answers. Did you catch my mistake or not? Someone equation. Okay, guys, that is my mistake. Everyone will get that as a bonus, the B part. Completely my mistake, guys. I didn't check it. I apologize. I'll correct the question here and we can go over it because it'll be helpful for your midterm anyway. So the part that will be graded is only the first one. Determine the value of K. Okay, so first, we need to determine two things. First, we need to know that it is non-negative. And the second, I need to know that the integration over the entire possible values should be equal to 1. Those are the two things I need to check. So here I know that the values of K, so for the first one, the first non-negativity, cross that out first, that's my mistake. So for the first one, we know that the values of X can be between the least value, the smallest value is -1. And if I were to put in -1 in there, in there, I would still obtain 3 minus it's 1, which is still positive, or the other way around, the maximum that it can go, it can be +1. And if I square it, it will also be 1, and it'll be 3 minus 1 will be 2. So now I need to know what K is. So the first one, I have to be able to prove non-negativity. And the second one, I need to be able to prove that that it's valid over the range. So here I have negative infinity to infinity, and I need to know, I can either do the non-negativity one or I can do this one. It has to be equal to 1. This looks a little daunting. It has the infinity values here, but don't worry, I don't actually need to compute it from negative infinity to infinity because I know that it's only supposed to be valid from -1 to 1. So in other words, I only need to compute from -1 to 1, K equals 1. Sorry, I should use correct notations, huh? And here I know that K is a constant. Remember, in integration, I don't need to integrate the constant. I can take it out. And then I can integrate only the 3 minus x squared. Integrate that, I can get 3x minus 1/3 x cube to the power of 3. Do you say cube? No, that's Indonesian, right? Cubic. From the limits 1 and -1, it should be equal to 1. Here I have K. I can substitute the x with 1 and -1. So I obtain that -3, -1, minus 1/3 of -1. This should be equal to 1. I'll continue it here. So now I have K 3 minus 1/3, yes. And 3 times -1, now I have -3. And -1 to the power of 3 is still -1 times 1/3, it's -1/3. And since it's minus, then I have a plus here instead. This should be equal to 1. And thus, I can have 8/3 -3, -8/3 equals to 1. K, these are two negatives, so now I have 16/3 equals to 1. K is 3/16. So now I know that the correct PDF should be fx, x equals 3 over 16, 3 minus x to the power of 2 minus 1 x until 1, 0, otherwise. So ignoring my mistake here, the follow-up questions to this type of problem could be of a variety of things. So now the first, in A, I asked you to please complete the PDF. So I have the correct constant. So now I already have the correct function. The follow-up from here could be one of two things. I could either ask you to compute a certain probability, like maybe what's the probability that my random variable is between, this case, we can only count from -1 to 1. What's the probability that it is between 1 and 0? Sorry, 0 and 1. What is the probability it is between 0.5x, 0.7? Whatever value I can have here, I can ask you to compute the integral. Or I could ask you to, for example, please compute the CDF of this function. Don't forget, the CDF is related to the PDF by integration. So you can just integrate it and obtain CDF. Either way, which you can do. So if I were to compute this correctly, if I were to, sorry, not compute, if I were to correct this typo in my questions, it was supposed to be, let me copy this to another slide. No. Let me copy this to another slide. Okay. And let me correct myself. What I meant with this question was not for you to determine this, but for you to determine p to the x should be less than a half. That was what I was going to ask you to do. But actually, even this one, you should be able to at least translate it into the correct integration. So when I say, what is the value of what's the probability that my x, sorry, this should be a large x too. So I had double mistakes here. So I'm going to give that as a bonus to you guys. This should be a large x, not small x. So you should actually still be able to compute this. So what is the probability? It's less than 12. Well, actually, what I need to do is, my limit is 12 here. My bottom limit, I don't have it. It's negative infinity because I don't have a limit here. And I can put in my previous completed equation, which was 3 over 16, 3 minus x power of 2 dx. I could do this. And since I know that there is no use for me to compute it until negative infinity, because the function is not even valid until there, I can change this to -1. And the top as well, there's no point for me to compute it until 12 because I know it's not valid until there. I can change it until 1. And there is no, and this is why the question that I gave you, it's a typo and it does not make any sense because this will obviously be equal to 1 because this is the entire range in which the function is valid. In order for us to get 3 over 16 just now, I actually already computed it. What is the correct value so that it'll equal to 1? Just now, I computed it. It should be equal to 1. So that's why this typo is a big mistake because it has no point for me to ask you to compute it to 12. Because the upper limit to 12, there's no use to compute it. I can change it to 1. The bottom limit to negative infinity, no point of computing it. I can change it to -1. So this is why this is a big problem. You shouldn't have to compute it. Although if you were to translate my question correctly to the correct integration, it will end up like this. So following that, with the correct question, x is less than half, then it's the same property, so the same principle, sorry. So if x is less than half, then my limits would be, once again, negative infinity and 0.5, and so on. But since I don't have a function that is valid until negative infinity anyway, I only have until -1, I can change the bottom limit to -1, sorry, and I can leave the upper limit to 0.5, and then I can compute this as follows. Then I can do the integration that we already did just now. And if you are interested to know the correct answer, it should end up to 99 over 128. You can check this on your own time by integrating this function with these limits. Apologies for that. Okay, last question from the quiz. This is obviously a random variable. Does anyone remember what type of random variable it should be? Oops.
Is it Poisson?
Yes. Oh, look at this nice pronunciation. It's Poisson. So we know that there is a rate. We know that there is some rate. Let's see. The restaurant receives an average of 20 reservations every day. So here, I know that the rate is 20 per what? For the interval of 1 day. So I can now compute the alpha as a multiplication of lambda and t, and I can obtain the alpha as 20. So if I'm going to correctly write the random variable, I can write if x is the number of reservations in a day, I can write that x follows the distribution, the Poisson distribution with the 20. So let's see what it says. The restaurant is open every day except Sunday. Every day has 12 operational hours. That matters. Find the probability of the restaurant receiving 10 to 15 reservations on a Wednesday. So what is important for us here? Which part? Not everything that I just read is important for us to solve the question. So the restaurant is open every day except Sunday. Does that matter in our computation? Keep in mind that I'm asking what's the probability of receiving reservations on Wednesday. Does it matter? It does not matter at all. Oops, someone answered in the chat as well. I thought it mattered. Oh, sorry, it does not actually matter. So if I were to ask you how many reservations it receives in a week, then yes, it would matter because Sunday should not be computed in a week and so forth. But since I'm asking for the time between 10 and 15 reservations, then it matters. Sorry, somebody's chatting me. As I per day is average of a total week. The average of 20 reservations is per day, so it doesn't really matter what day it is. It's 20 per day. So now we want to compute the probability that x is between 10 to 15. So here, since I don't really know, oh, it says receiving 10 to 15. So 10 is included, 15 is also included. Since it is Poisson, then actually I can just compute the sum of x equal to 10 plus equal to 11, and so forth until Px equals 15. Don't forget that the Poisson distribution has a PMF as follows: alpha, alpha, x, factorial. So I can just fill this in with e to the power of my alpha is 20. Then I have 20 to the power of 10, and I have 10 factorial, and so forth. And if you want to check it, the final answer should be around 1515, and so for 0.1515 and so forth. Okay, so that is the end of the quiz discussion. I think, yes, that's it. Does anyone have any questions?
Miss, just out of curiosity for the number 3, if the question we change the question into like the interval between I remember it was -1, x, and 1. What if we change the what do you call the lower equal without the equal, so without the line under it? What
Sorry, what do you mean?
It's the number 3 one.
Oh,
Yeah.
I think you
so
become less than
instead
rather
of,
than less than equals.
yeah,
Larger than
so
those kind of things.
so it's less than and equal and less than and not.
Does it
Are you
matter in the
homework
equation?
in the, yeah, okay. So that is the specialty, you can say, about a continuous random variable that is defined using a PDF. It does not matter if you include it or if you do not include it. So if like in this case, it matters. In the example here, it will matter what it means because I'm using a PMF to compute it. But in the case of a PDF, since we're computing the area under the curve, it does not matter. So if, oh, I'm giving you a hint for the homework, aren't I? It doesn't matter.
Okay, thank you very much.
Okay. Any other questions? I'll give you like around 1 minute to maybe get some inspiration if you have a question. And I'm going to take a drink break. No questions yet? Okay, if anyone gets a question during the explanation, please unmute your if it comes behind, if it comes later on, don't be afraid to just unmute your mic and let me know. So I prepared a series of recap slides or review slides, which I have found it useful for many of my students, that sometimes all of the material looks quite daunting if you put together all of the PDF files on Scale. So when possible, I have a habit of putting together a review, so to speak, so that you can look at the material in a more holistic way, and you can realize that the main concepts aren't that difficult. They're not too many of them, but you need to know which one, when you need to use which one, more or less. So this is going to be very brief. I will not go into very much detail. These slides, actually a more comprehensive version of these slides will be available on Scale at 4 p.m. today. Okay, so remember that what we are trying to do in this course is as simple as I want to change the bunch of data that may be shown to me in a bunch of numbers, maybe in a bunch of numbers, or maybe in a table of so many different types of data. I want to change it into something that is meaningful for me. So that is what we are trying to do in this course. Simple as that. And in order for us to understand, we need to know how exactly each type of data we have is measured. We have 4 different scales of measurements. If you remember, we have the nominal one, ordinal, interval, and ratio, starting from the least to most precise. If you want to determine which type is which, you have to be able to identify some characteristics that they have. All of them should be mutually exclusive. For example, if I were to measure height, if someone is 165 centimeters tall, there should be no way for him to also be 166 centimeters tall. This is what it means by mutually exclusive. So if we are taking data of gender, someone should only fall into one category. I'm not trying to go into the political debate of it, but that is the concept that I mean by mutually exclusive. Next, we have a logical order. So in the argument just now, when we were talking about gender, female and male, you cannot put one above the other. No, you cannot. So you do not have a logical order. Same goes for juices at Fasilcom. You don't have a logical order. But if you're talking about anything else, like maybe scores of your end score in Statprob, A, B, C, D, E, there is some sort of order to it. Next, we also have equal distance. Is the distance between 3 and 5 the same as 7 and 9? If it does, then it might be the interval or ratio scale, whereas for ordinal scale, it is not. And lastly, in order to distinguish interval and ratio, you need to determine what 0 means on your scale. Is it just another point, or does it mean that you do not have a measurement? If it means you do not have a measurement, then it is the ratio scale. So using these measurements, we can get the data, and from these data, we can do statistical operations, either to describe your data or to infer information from it. Before we can infer information from it, we need to be able to describe it clearly and concisely. So we have a couple of basic things to know: describing, summarizing, and so forth. So for the describing data sets, don't forget we have multiple ways to show them because humans are very visual. So we like to use many different types of visualization. We can visualize it with absolute values or relative values. We can also display it using group data or ungrouped data. There are many variations in visualizing our data. So now, what is the data that we are trying to show? So when I'm doing a study, there is no way I'm able to actually ask every single person that is my population. So in order to conduct a statistical study, we need to take samples from our population. There are many ways to do so. Random sampling, systematic, stratified, cluster, and convenience sampling are covered in this course. And after I sample after I do the sampling and I obtain my sample, then I can start taking data. But actually what I'm taking is not representative of the population yet, because at the moment I'm only taking a statistic from my sample. The parameter is that is correlated to the population, which we want to infer later on. A parameter to a population is as a statistic is to a sample. Next, after I obtain these data points from my sample, then I need to be able to show how the numbers fall. Like, is it large variance? Where do the data congregate, and so forth? So in order for me to describe this data to you, I can use these types of measures. I can use central tendency to tell you where they are, most of them. I can give you measures of variance to show you how far they go to the left, to the right. And lastly, measures of position for you to understand what do you mean by you are 165 centimeters tall? Where are you on the scale? So these are the 3 types of summarizations that you can use to describe what data you have. When I'm talking about the height, like 165, the one that I just mentioned just now, then in order for me to be able to fairly compare different types of data points, if I have two different distributions, one is x1 with a mean of x1 and the other one has a mean of x2, in order for me to be able to compare them, I have to be able to compare them on an even playing field. So I would need to transform it. For example, here we have a data point here and a data point there. If you look at the absolute values, obviously the one on the right is larger than the one on the left. But when I map these to the same scale, and apparently the red one, it was above the mean, so there is also above the mean, and the x2, sorry, the green one is no longer higher than the red one, because if I map them to the same scale, then they are not corresponding to their absolute values. So up until now, we've only talked about the scores of every individual measurement, every individual variable, but we also sometimes want to know the correlation between one variable and the other. In order to understand this correlation, we can use scatter plots. But from the scatter plot, we can only obtain the notion. You can get a feeling, oh, they have a correlation. Oh, the correlation is positive, it's negative. How straight of a line is it? You can get a good idea as to how they are correlated. But if you want to actually give a objective analysis, you need to use a measurement that is numerical. This is the correlation coefficient that you can use. You can either use the Pearson R or the Spearman rho. The Pearson R is using, you can either use raw data, you can use z-scores, you can use deviation score, and this can be computed for interval and ratio scale only. The catch is that you have to have paired observations for every single data point. For the Spearman rho, it is using the rank information and thus can be an approximation towards the Pearson R. Be careful not to confuse correlation with causation. Okay, so now we have all our data. We have how they are correlated. We have how large they are. We have where they are congregated. Now we are going to start to compute the tendencies, the probabilities. What are their, what do they tend to do? So we are going to learn about the probability. So here we have to determine both sample space and events. So when I'm talking about a sample space, I'm talking about every single thing that can happen. When I'm talking about the event, I'm talking about what actually did happen. Since we're talking about sets, then we need to recall some theories: complements, union, intersection, subset, and proper subset. You can look into this one more time. Please don't forget it because it is quite important when you are trying to visualize events. And if you recall, I once asked you, what is the probability of me obtaining a 3 if I were to throw a dice? And then one of you, I don't remember who, said 1/6. And I said, yes, if we assume that each point in the sample space is equally likely to occur, then we can compute the probability of 3 coming up as 1/6. What this equation means is more or less that here, n, this is my sample space. I need to know what possibilities are there. And these are the members in E. What exactly did happen? This is also called the favorable event, or event in consideration, event in computation. What are you actually talking about? It is a fraction, because the probability must be between 0 and 1 anyway. So you need to compute the fraction. Sometimes we cannot only consider events on their own, but like in our quiz, we had conditional probability because we wanted to know, wait, what if I already know this? Then what is going to happen with the second event? Like if I were to ask, oh, what is the probability of Zahran getting an A in statistics and probability. I would not really know, but if I were to know, oh, Zahran got 98 on his first quiz, then what is the probability of Zahran getting an A if I already know the prior information that I know, given I know that Zahran already got a 98 on his quiz. So in this case, I can obtain the conditional probability. Last time I used a yellow highlighter. This time I'll use the same so you don't forget. I used a yellow highlighter to show that this is the conditional probability. Please do not forget this because this comes up many times, as you recall, in the following materials. So in the example that I just talked about, the event in which Zahran got 98 is the conditioning event, and the probability of getting an A and quiz is EF on top, and this is the probability of getting an A given I already know he obtained 98 on his quiz. So don't forget that in this case, why is this PF? Because the sample space changes. I no longer need to compute the sample space as all possible events. I only need to know the events in which the conditioning event is true. In this case, in the case where his quiz is 98. So my sample space here will change. So knowing that, and knowing the set theories of an event and its complement, we now can sum up. If I'm trying to compute the probability of a certain event, I can compute it as a sum of the events in which something else happens. When I'm trying to compute E here, when I'm trying to compute the probability of E, I can consider event E when F is valid, and E when F is not valid. And since they are mutually exclusive, the resulting probability is a sum of both. We already went through in class how we can end up here because we can switch around the previously highlighted yellow equation. We can also sum up the law of total probability, and thus we can obtain this rule. And finally, we have Bayes' theorem. So if I know a conditioning event, the prior probabilities, and I know the likelihoods of A happening based on those prior probabilities. So I know something, C1, condition 2, and so forth, and I know the probability of something else, A, happening based on those conditions. If I want to compute the other way around, instead of computing A based on the conditions, I now want to compute the condition based on A. Then I can compute it using the Bayesian theorem as follows. On top here is the opposite. So here it says PCA, and here it's the opposite conditional. We already went through how we can equate this and this. And the bottom is the law of total probability. By summing up all of the complements, we can add them up together. And this is the total probability of A. Short pause. Any questions? Let me check the chat. Not yet? Okay, I'm just afraid that I'm talking too much and you're getting lost. Okay, I'll continue. So after we talked about probabilities, we then talked about, but what if I don't care about every single event that might come up? Instead, I want something, I want an abstraction. I want to encode it in such a way that now instead of talking about exactly what happens, I have a certain number. Then I can use random variables where I assign a number to every output. I'd like you to remember that this function is not one-to-one because I can assign multiple outcomes to the same number. And if I have random variables like this, I have to be able to describe how they are distributed. I have 3 different functions that I can use to talk about how this random variable x is distributed. So first I can use the probability mass function that will give me the probability of my random variable being a certain value, the cumulative distribution function giving me the probability of it being up to a certain value, and the PDF giving the probability between 2 limits, the upper limit and the bottom limit. The PMF and CDF can be used to compute the discrete random variables, and the CDF and PDF can be used to compute the continuous random variables. What are these? We have discrete and we have continuous ones, but before our midterm, we only had the chance to look at some special types of the discrete ones only. We have 5 different types of discrete random variables that we looked at. We first learned about the Bernoulli random variables. As I mentioned, the Bernoulli random variable is not very useful on its own. It's more as a building block for us to be able to define the following ones. Like, for example, Jerome, do you like K-pop? You're the only one with your camera on my screen right now, so you're the one I asked. Do you like K-pop?
Not into K-pop, actually.
No. Okay. So just now, Jerome could have said yes, and he could have said no. So here is a Bernoulli random variable. The probability that a student likes K-pop can be yes, can be no. That's the only outcome that can come out of this random variable. So let's ask some more people. Saddam, do you like K-pop?
No, miss, I don't like K-pop.
Okay. Alif Yandra, do you like K-pop?
No.
No? Okay, I'm gonna try to find someone who does. Bagus, do you like K-pop?
No, miss. I don't.
No? Oh my God. Okay. Can I ask some of the girls maybe? Hanifah, do you like K-pop?
Yes.
Oh, yay, finally. So just now I asked Jerome, Saddam, Bagus, and Hanifah. So B now is the number of students that like K-pop in a group of 4. Hey, I want to ask one more person. Jerome said that I have to ask Abraham. Abraham, do you like K-pop?
Yes, miss.
Yay! Okay, so I had a binomial random variable because I repeated my Bernoulli trial 5 times. So now I have a binomial random variable which describes the number of students that like K-pop in a group of 5. So it's important for me to determine 5 because I need to be able to limit my trials at a certain number n. So here just now, I can compute the number of students and I can compute the probability of the students that like K-pop in a group of 5 to be 1, 2, 3, 4, and so forth. So just now, when I was looking for someone to like K-pop, I had to repeat my Bernoulli random variable, my Bernoulli trial 4 times. First, I asked Jerome, he said no. Then I asked Alif Yandra, he said no. Wait, I asked more people, didn't I? And I just forgot someone, didn't I? Sorry, who did I forget last time? So I asked Jerome, then I asked Saddam, asked Alif Yandra, and then I asked Bagus. Then I asked Hanifah, right? I think I remembering your names correctly. So just now I had to repeat a certain number of times until I obtain yes. So this is our geometric random variable. So let me repeat. Bernoulli is when I do 1 and I can get either yes or no. Binomial is when I repeat the Bernoulli n times, and I need to know how many times I get a yes. Geometric is how many times do I actually need to do a Bernoulli trial until someone gives me a yes. The next one is not a direct Bernoulli one, does not directly use Bernoulli trials, but in a group of these 20, how many students are here today? 21 students that are here today. And let's say I know that 6 are a special kind that like K-pop. And if I take at random if I take at random 2 students to accompany me to watch the upcoming, I think there's going to be an online SM concert soon. So if I'm going to choose at random 2 students to accompany me to watch this concert, what is the probability of me choosing students that actually like K-pop? Since I'm choosing 2, what's the probability of me getting 0 students that like K-pop, 1 student liking K-pop, or 2 students liking K-pop? So here I have a group of 21 students in this class. I know that 6 of them like K-pop, and I'm just going to select 2 of them to accompany me to watch an online concert. Okay, and the last one, if I were to compute, if I know that there's a rate that there are usually 20 students per cohort, so per year, that's what I mean by cohort, that likes K-pop, this is now my rate, then what is the number of students that like K-pop in the entire Faculty of Computer Science? If I were to translate these examples that I just gave you in the correct term, then I can write these random variables as follows. I'm not going to go over them, but here are some review slides for us to compute the particular properties that every single random variable has. You have to be able to compute the expectation, the variance, and PMF/CDF for every single one of these. So in the last weekly reflection, I received some of you guys' comments saying that it's a little confusing sometimes to determine which random variable you need to use, even though you feel like you understand the difference between all of them. So go ahead, take a look at this particular case. I'll give you around 2 minutes just to read it. You don't need to solve it yet. And tell me which random variable this is. Anyone? What type is this? Oh, I see someone geometry. Not quite. Oh, I see chats. Okay. So I have some answers here. Let's try to go through it together. So I know that this archer, the possibility when this archer is to shoot an arrow, I either have, first I know that the possibility is either hitting the bullseye or not hitting the bullseye. So we know that it is building on a Bernoulli trial. We know that every time the archer shoots his arrow, the probability of hitting bullseye is 0.09. And we assume that every single trial, every single Bernoulli attempt is independent of each other. It's important. Constant probability, independence. Next, we know that the archer shoots a total of 9 arrows. I know that he's only going to do the Bernoulli trial 9 times. Thus, I can write, don't forget that I need to correctly answer using the correct statistical notation. So first I need to determine the random variable. Let's do it for everyone. So here what I want to compute is what's the probability that there are 2 total bullseye. So among 9, how many successes does he have? How many times does he actually score or obtain the bullseye? So here I can determine X is the number of arrows that score bullseye. And I know that X will follow a binomial distribution with 9 attempts, and each attempt has a probability of 0.0. Thus, for A, what I want to compute is the probability of X being equal to 2. B, at least, what does that mean? P has to be X larger and equal to 2, because it says at least 2 arrows score bullseye. And C, what is the expectation of the number of bullseyes scored? This one, it's quite simple. I just need to compute the PMF, which I don't know it by heart. It doesn't matter. You guys are also going to have an open everything test, so you can go and peek at the binomial random variable PMF, and we know that it is a combination of nx, px, and so forth. I don't know it by heart either, so it should be something like nx and the p. Oops, not that one. P to the power of x and 1 minus p. Okay. P to the power of x times 1 minus p, so 0.91 to the power of 7, I think, something like that. Here, since it's larger and equal to, and we do not have any function that goes larger, we only have it less than, so we can now compute the opposite. 1 minus px equals 1 minus px equals 0. Don't forget, we can compute this, we can compute that. And for the expectation as well, I think you can just, is it NP or something? Expectation is, yes, NP. So you can just compute N times P, 9 times 0.09. Is that 0.018? Is that right? Wait, that was dumb of me. Not 18. 9 times 9 is 81. Lesson of the day, use a calculator. 0.81. And that's it. That is the example 1 solved here. Next, don't forget my bullseye guide. I'll give you some time to, if you have any questions on the previous one, you can ask it now, or if not, you can go on to this question. 2 minutes to read this question. Okay. Any ideas here? We're still talking about the same one.
Is it geometric, Miss?
Geometric. Yeah, let's look at this one. Okay, let's go into it together. We now know still the probability is P and it's independent of each other. And now we know that he's shooting a series of arrows. So we know it's a series of Bernoulli attempts, but this time I don't know exactly how many times. But what I want to compute is that the first bullseye, the first hit, the first success is scored with the fourth attempt or the fourth arrow. So here I know if X is the number of attempts to hit a bullseye, I can compute X as a geometric random variable with a probability of 0.09. And once again, what I'm trying to compute is what's the probability that the first bullseye, the first success, is the fourth arrow. So what's the probability that I need exactly 4 attempts to get that first success? Don't forget that the first successful attempt is calculated as well. So if it's the fourth one, that means the fourth attempt is also calculated. X equals 4. I do not remember the formula for that as well. 1 minus P, I think, is it? Yeah, 1 minus P. Where is it? Oh, it's a sum of, the CDF, sorry, the CDF is the sum. That means the PMF is this only. P, 1 minus P, R minus 1. So P, 1 minus P, and this is X minus 1. So here we have 0.09. Here we have 0.91 to the power of 3. If any of you have access to a calculator, please help me out with that. It should be 0.06 something, I think. So you can finish that off with your calculator. Okay, another 2-minute pause for anyone that would like to ask a question of the previous question about the previous problem or ask a question about this new one. Any question? Any questions or any guesses as to which one this is? I underlined an important keyword. Someone is in the chat. With replacement, that means it's independent and therefore it's geometric. That's what Kevin said. So since we know that it is with replacement, so I know that that's the first thing that I know is exactly what Kevin said. It's independent from each other. It doesn't matter what I take in the first trial because I'm going to put it back. So it doesn't affect the second drawing and so forth. Next, since I replace the card that I take, the number of cards in the deck also stays the same, and thus the probability also will be the same at every time. So here I know that usually one pack of cards consists of 13 times 4. Yes, 13 times 4. You're not considering the jokers and so forth, okay? So there's 13 times 4 shapes. What do you say shapes in English? Is it shapes? Spear. I can't draw. Forget this. So we have around 52 cards in total. And what I'm trying to talk about here is the probability that the heart is drawn. So I know for the probability, if I determine X is, the first success at drawing a heart, I need to compute that actually the possibility of obtaining a heart itself is 13 out of 52 because heart, there are 13 of them. So I can also write X as a geometric random variable that follows a probability of 13 over 52. And calculate the probability that the first heart is obtained on the third drawing. So what's the probability of X being equal to 3? I can just use as well here the geometric equation. Oops, I didn't need to go that far. You can just go here, right? P1 minus P, X minus 1. So here it's 352. And then there is 39, 52 times 2. To the, not time, sorry, to the power of 2. Once again, anyone with a calculator, you can please go ahead and write this down for me. I don't remember. I cannot compute it in my head. Okay, one more break. No, there's 2 more questions. I apologize. Next question with a short break to ask questions and read the problem.
This out of curiosity, actually, like the 2 question before the Archer one, if we are tasked to calculate, it is I remember it was spot on the 4th attempt, right? What if we're tasked to maybe like the possibility of within the 4 attempts it can be success?
So within the 4 attempts, that means it can either be on the first, the second, the third, and
Exactly,
the 4th,
yes.
right? So you need to sum up the probabilities of it being the first, the second, the third, and the 4th.
Also, we only need to sum up all of them until the 4th one.
Because it's the CDF, right? So when you translate those words, so you're saying like, what are the probabilities that it happens within those 4 trials, right? So it should be anything up to 4, right? So that is a CDF, right? Anything up to a certain value, right?
Right. Mm-hmm.
Yes. And if you recall, the CDF of a discrete random variable is just the sigma, the summation of all possibilities up until that number.
Okay. Got it. Thank you.
Okay, so for sake of brevity, yes, sake of brevity, I'm just going to skip over to the solution here. Oh, sorry, let's not. Does anyone want to offer their opinion? What is this? Which random variable this is? Anyone? Anyone in the chat? Is it hypergeo? Or is that the new term? Hypergeo. So it's the the abbreviation. Yes, indeed, it is a hypergeometric one. And since blah, 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 what is the jury? So I know that I need to, oops, what is this? We don't return those people. Okay, good wording. It's as if you're taking cards, but you're taking a person and putting it back. But yes, you're correct. Since we are not replacing them back to the pool, that means that it's without replacement. And thus we need to determine the possibility as such. I apologize. I think this last sentence does not even matter. Oops, where am I? Ah, there we go. I don't even think that last one matters. So here we go. We know that this is the hypergeometric possibilities. You can compute it as follows. Last one. Suppose that the number of errors in your, what programming class are you currently taking? Is it data structures? No? Is that what you're currently taking right now in this semester? Did I just traumatize you? Suddenly there's so many chats. Yes. Okay, so say you're submitting your code for a programming task, and the number of errors in your software, in your submission, your program, it has a Poisson distribution with the parameter rate of lambda equals 3. So in this case, we know that the lambda is 3. There's no point in me asking you what type of random variable it is. It's written right here. So we know that the lambda is 3, and it says that the number of errors in a piece of software, in one software, one program. So here we already know that the t is, oh, what did I just write? T is 1. So what is the probability that the piece of software has no error? First, I need to solve this correctly using the correct notation. So allow me to write the correct random variable. So x is the, number of errors in a software. And x follows the Poisson distribution with alpha equals lambda times t, in this case 3, like that. Don't forget to do this step because that's the correct statistical notation. And here what I want to compute is what is the probability that there is no error. And for the next one, what is the probability that there are 3 or more errors? Once again, we don't know any probability of larger than, but we do know the probability of the less than. So I can do 1 minus px equals 0 minus px equals 1 minus px equals 2. And here is the solution already computed for you. Okay, last chance. Any questions? I think that's the end. Yes, that is actually the end of my review slides. Any questions? If not about the material, any questions about the midterm, or
Yes, I
or
have
you'd
questions.
rather not think about it yet? Yes, go ahead.
Will the